Today's challenge, we have a component called an oxyarm. This is a medical device. If you've ever seen any of our other CAE specialists do a demonstration of our CFD software, SolidWorks Flow Simulation, you might have seen this. But basically what we're going to do today is take a look at a couple of different components in this design that are injection molded. The first is a mushroom, and I'm going to show you two different methods of analyzing this very small part. The first is using a shell mesh, the second is using a solid mesh, and then I'm going to show you how easy it is to do a design change and re-update your plastic mold flow analysis. The second thing that we'll do would be analyzing the flow of a multi-cavity mold. This would be functionality that we would find in SolidWorks Plastics Premium. And then the last is I will show a third model, the diffuser, where we analyze multiple gates. So let's take a look at our oxyarm here. This is the headset. Basically, on the back end of the part, back in here, is where we have our oxygen input. And then down here in this mouthpiece, this is where the flow of oxygen is dispersed towards the patient's mouth and nose for breathing. The components that we're really interested in, however, are just in this the mouthpiece for the entire oxyarm assembly. So the mushroom, that's the first part that we're going to look at, is this component here that I'll highlight there in blue. And that's what we're going to do our first look at SolidWorks Plastics with just the capabilities of Plastics Professional. And then after we've gone through that, we'll analyze the diffuser. So let's go ahead and dig into this particular part here. The first thing that I'm going to show you is basically the SolidWorks Plastics product is just an add-in to SolidWorks. Just like all of our other simulation tools, it allows us to work directly on our designs right within SolidWorks with an interface we're familiar with. So I already have my plastics add-on turned on. From there, what it does is it gives me an additional tab on the command manager as well as an additional icon over above my feature manager tree. I've turned on an option so that Plastics recognizes I have multiple configurations in a part. So let's just go ahead and add a new configuration. We'll call this our webinar model. And I get a warning that I need to reload the Plastics project. That's completely expected. That's basically telling me, hey, you've changed your model. You need to do something with it. So let's go ahead and start through this. What I'm going to do is, first step, just create a shell mesh on this part. A shell mesh is nothing more than a surface mesh around the entire surface area of this part. It's a great way to do a first pass analysis. Just help get us started with analyzing our injection mold flow of the plastics part. So as I start this, you'll see I have a triangle size. This would be analogous to the mesh size that we would do in finite element analysis. If I click the mesh button, very quickly I get a representation of the surface of the part. Now what you'll notice here is I have a fairly large triangle size, and clearly these features don't quite look like the part. So what I can do is refine that mesh size just a little bit, mesh it again, and you can see there that it looks a little bit closer to what we're really looking for as far as the true volume and shape of the part. I have some options for refining the mesh. I could do it manually if I click the Set button, or if I turn on this option here for Auto and remesh it. SolidWorks Plastics recognizes where I have curvature in the part and automatically refines the mesh, or these triangles on the surface of the part. It does it for me, so that's a great little feature to do. So we'll go ahead and accept that. And two of the key elements here based on the mesh are bad elements or very bad elements. We have some guidelines for the maximum values that you would want to see in those boxes. Since there's 0%, we'll just continue on. And then because I'm running a license of Plastics Premium, these tools here in this feature manager tree, these are methods for me to go in and manually modify the mesh. So I have a lot of additional controls above and beyond just meshing this part right within Plastics. So we'll accept that. And now the next step that I need to do would be select the polymer, now that I have my mesh for the model. So let's go ahead and open our database. The SolidWorks Plastics product has a database of close to 5,000 commercially available resins, and they're sorted by category. Now this part happens to be injection molded with Delrin, which I know happens to be a POM, or a polyoxymethylene. So I could hunt for my product, the product category for POM, and find the Delrin that I'm looking for. It happens to be a DuPont resin. Or what I could do if I didn't want to search through that, I could click on Find and just type in the name of a resin, and it would show me where those are at, which material category they're in. For the Plastics Professional product, you just have the database available. And for Plastics Premium, you have the capability of creating your own materials. So let me go ahead and cancel that and show you another function here. Since I've already used the particular resin for this part, there's a list. If I just right-click on the polymer, it's always available to me for recently used polymers. So we'll go ahead and assign Delrin 500 to this. Next thing that I need to do is open the settings for the injection mold machine. The default for Plastics Professional is just a single machine, but Plastics Premium, you get this library of several hundred different manufacturers for injection mold machine settings. The biggest thing here that we're really looking at would be the maximum shot volume, maximum injection pressure for our mold machine. So we'll go ahead and choose the default machine, which, believe me, is more than adequate for this tiny part. The next thing that I have to do is open up my flow settings. SolidWorks Plastics recognizes the volume of the part and gives me a recommended filling time for how long it would take to inject the plastic into this volume. And then the melt temperature and mold temperature, those are basically the recommendations from the resin manufacturer on how you should operate your injection mold machine with that particular resin. If we were doing a filled material, for instance, like a glass-filled nylon, we can calculate fiber orientation by either weight or volume. And if you're doing a co-injection or overmolding, you can specify additional materials there. So we'll just accept our defaults for our flow settings. Last but not least will be our gate selection. All we have to do is tell Plastics where the gate is going to be located. So I can just click at that node, which is going to be at the center of that face, put in a recommended size, 1.25, and then add the gate. And that's all there is to the setup. So let's go ahead and run our flow analysis. I'm going to move these settings around a little bit so you can see what happens on screen. And you'll notice that as this model is running, we're going to see real-time what's happening to the flow of plastic in our part. Now this is really nice. If I happen to look as the plastic is flowing into the component and I see an issue in the design, I could suspend the run, go in, modify whatever the parameters are that I had, and then fix that. So here what we'll see is once the fill of this component is finished, I get the output that I would need to tell the injection mold maker, basically clamp tonnage, the maximum injection pressure, things that they're going to be interested in for processing the component. So let's go ahead and exit that, and let's take a look at some of the features inside Plastics Professional. First you'll notice is I have a results advisor on the right-hand side of the screen. This shows up at the end of every plastic simulation that I do, so if I'm not an expert in injection molding, anytime I change any of these plots, I get a real-time feedback on the results advisor for basically what this plot would mean to me as a designer or an engineer. So I could read down and see, fill time. What does that mean to me on this particular part? It's basically like a quick way to get into the help file. So I'm going to go ahead and close that, and let's start taking a look at some of the features that we have once we have our plot. First would be to just play a plot. So this would be the fill time. And you can see if I slow that down, that's the melt flow front that we're seeing traverse through the part from our gate to the outside edges of the part where it's going to fill right at the end. I'll go ahead and stop that. Other things that we might be interested in as designers are weld lines. Now, since this is a fairly uniform part, we're not going to have too much in the way of weld lines, but what a weld line is where the flow front of the plastic is separated and then rejoins somewhere after the gate. And why a weld line is important to us is it can be thought of as like a defect in the part. It can cause cosmetic issues on the surface of the part. So these are things that we would want to know. For instance, if this region right here where we see the weld lines very close to the gate, if that is structurally important right there, we might have to do some things with our design to make sure that we can move those weld lines around. Another thing that I'm going to turn on is the air traps. You can see I've got 4 different purple spheres that show up on this part. Those are indicating where the air would need to be vented from our mold. Air traps are, well, they can be a very bad thing in injection molding. You can think about injecting very hot plastic at a high pressure. If you cannot vent these locations in the part, you can get something that's called dieseling in the injection mold industry, where basically you get a burn mark on the surface of the part. You actually get combustion out of the hot compressed air. So let's go ahead and turn those off. And then you can see any of the other plots that we would get here. For instance, the volume shrinkage at the end of the fill. It gives us a result of approximately how much shrink might occur on the outside of that part. Now I should note that I only analyzed the fill of this component, stage 1 injection molding. I didn't do anything beyond that. And then last would be sink marks. All right, so that's a very simple model using shell mesh on the part. So let me add another configuration here, and we'll do this one. We'll call it webinar solid mesh. And yes, we're going to start a new project. Here, what I'm going to do, go into my settings. Solid mesh, this is rather than just meshing the surface of the part, it's actually going to mesh the entire volume. As you can see here, if I had cavities plus inserts, this is where I would define it in plastics. And I'll go back to close to the simulation settings for this that I had before. So the first step in generating a solid mesh is basically mesh the surface of the part. And then once I have that completed, what we're going to do is choose the type of solid mesh that we're going to develop. We have a couple of different meshing technologies here. I'm going to use a hybrid tetrahedral. And basically when I click the transform button, that takes and meshes from the outside surface of the entire part to the volume. As you can see here, now I have solid elements throughout. It's really nice. I have a couple of different element types. Let's see, where's a good place to show it. So what happens when I make a solid mesh on this part, I have what we would call brick elements on the outside and then tetrahedral elements on the inside. And the reason for this is it gives us a better representation of the flow front and the pressures that are happening as the plastic is being injected into the part. So we'll go ahead and accept that. And we'll rotate it around. Same thing as before. I'm going to choose the same polymer and choose the same injection mold machine. Choose the same settings for the flow and go back in and once again choose a gate location like I did before. Add that in and then just run our flow analysis. Now again, since this is a fairly simple part, it doesn't take too long to run. And if we were to go back in and compare the results from one run to the next, you would see that because this is a very simple part, we're not going to have much variation. Now I mentioned earlier that the shell mesh is great for first pass analysis. If you have a lot of variation in wall thickness of your part, then you would only use the shell mesh as a first pass. You would really want to analyze that with a solid mesh just to get your final results. So we'll let this model finish. By the way, if you have any questions, feel free to type it in the questions panel, and we'll try and answer those as this analysis is running. Okay, your screen should update here very shortly with the finalized results. Okay, and like I said before, we get the important things that we would need to tell our injection mold manufacturer: clamp tonnage, injection pressure, temperatures, and so forth. And all the same output as before. All right, let's go ahead and switch over to looking at a multi-cavity part. So here I have a setup. This is a multi-body part file. I have 4 different mushrooms. This basically I'm building a 4-cavity mold. And you can see, excuse me, I already have a sketch built in place, which is going to represent the runner system from the gate up here at this point to the injection points at each of those 4 different parts. So let's go ahead and set up just a shell mesh. Again, I'll go roughly into the same settings I had before, and we'll do a surface mesh on all 4 of these components. That's step 1. And then now what I'm going to do is use some of the functionality that you would get in SolidWorks Plastics Premium. I have a question. Does the model analysis take into account carbon or glass flake additives to the base polymer? Yes, if you have filled polymers, we can set that up as we're doing the flow settings, and I'll do that again. So let's go into the runner design. We have a couple of different, or actually several different shapes that we can use for our runners, and we'll just set this up very quickly here. We'll start with a couple of different sizes for the first component and build in with basically beam elements, if you will, the size of our runner system. So let's select a couple of other legs here. We'll bring those in. And let me make sure I get the orientation on that correct. Okay, there we go. We'll bring in these other 3. And there's our runner system for our 4-up tool. Once I have that, we'll just use the same polymer that we had before, same injection mold machine. Then our flow settings here. For your question, yes, if I had fiber orientation or a fiber, I could add that in by either weight or volume to the resin as far as my flow settings. And then, of course, we have to specify our gate location. That should be a 2.5 millimeter gate, and we'll put it right there, right at the gate. Add that in. So that's the setup for this, and then all we need to do is just run our flow analysis on our gate and runner system. All right, any questions, any other questions while this model is running? This should take about 45 seconds or so. All right, no questions. So tell you what, while this is running, let me pull up a PDF file and try and minimize this on screen a little bit so you can see a number of things going on. There is a feature matrix for SolidWorks Plastics that compares the different features that you get between the 2 different products. If you're interested in having me email this to you, I'll give you my contact information at the end of the webinar. I'll be happy to send it to you so you can get a good understanding of what capability exists in the 2 different levels of products. And then you can see in the background as this model is running, We're getting the real-time feedback of what's happening through our gate and runner system, and then the injection mold of this 4-up tool. And let me switch to the second page of the feature matrix for plastics. Almost finished on the fill of this multi-cavity mold. All right, let's go ahead and close out our PDF file. And we'll close out our results advisor here in just a second. There we go. So no different than before. I have all of the same different plots or results output that I can get. And if I take a look at the flow speed, let me slow down this a little bit. We can see the flow of the plastic through our gate and runner system and then into all 4 parts individually. Now if this were a family tool where I had, say, different halves of maybe an electronics enclosure, I know we showed something like that at the 2013 rollouts, but bottom line is if I had a family mold where the components in my injection mold tool had different volumes and would fill in at different times, there is a function in Plastics Premium called runner balancing where I can actually run an algorithm to balance the size of these runners so the components fill at roughly the same time. All right, let's go ahead and exit out of this, and let's take a look at a little bit more complex model. This would be the diffuser. All right, so now I've pre-prepped this particular model by putting a split line on this face, and what we're going to do is basically put in gates at these 3 locations. So let's go ahead and start. We'll add a new configuration. Start a new plastics project. And we'll go ahead and do this with shell mesh since it will run slightly faster than doing a solid element. So we'll just go ahead and accept a couple of defaults here. Make sure we get a decent representation of the volume of the part. As I rotate it around, I can check and make sure that features such as there's a thin rib on the inside or the ID of this diffuser. That's where the elbow for the oxy arm gets put in. I want to make sure that I can see that. Since it is in the part, I should be good to proceed with the rest of this analysis. So there's our surface mesh. And we'll choose the same polymer as before, Delrin 500. Choose the same molding machine. Here, let's go ahead and change, see if we can inject the plastic a little bit faster than the recommended time. This would be important for trying to optimize our cycle time. And then as I mentioned, we're going to do multiple gates. So we're going to put in 3 small gates. So what I'm going to do is zoom in on the part here. There's 1 gate location. There's my 2nd gate location. And here's my 3rd gate location. And that should be it. So let's go ahead and analyze the flow into this particular model with 3 different gates. All right, we have another question. Will the software predict the optimum location and number of gates? Yes, the software will predict where you should put the gate, but it is based on the center of mass and the volume and surface area of the part. Basically, I would look at it as giving you a decent starting point. You can tell it how many gates that you would want to put in and then have it give you those locations. In my experience, you would still need to tweak it, mainly because like I said, it's going to give you the location that it thinks you should put the gate. It won't necessarily put the gate in a location that you physically could build a gate into your injection mold tool. Does that answer your question? All right, good. So here we can see once we finish this analysis with our 3 different gates, we'll go ahead and close this out. We know what ton mold we would need to do for our clamp pressure. Let's take a look at a couple of things here. Let's say, for instance, you have a metrology department or someone that needs to measure the flattens of that top surface of the part. What I'm going to do is go into our measure tool. I'm actually going to turn on an XY plot. What I'm going to do is pick a few locations around this face. And what this allows us to do would be get an idea of how much sink around this part might affect us. So if I make this a little bit larger, we can see that we're ranging from somewhere right around 12 thousandths of an inch to not much higher than that. And then on the node list, we get all this data here. This gives us an indication of what the flatness of that part might be. Now we can take this data, give it to our QA department, and this is what we could roughly expect from that part. So if you were concerned about variation of more than about 5/10 thousandths of an inch, that might be something to know in advance. Of course, this is a fairly simple part, so it's not going to vary that much. Let's go ahead and turn that off and turn off our measure tool. The nice thing about using multiple gates is we get this gate filling contribution. So we can see gate 1, this gate here, this is the volume of the part that's filled by gate 1. The blue is the volume of the part filled by gate 2, and then 3 obviously by gate 3. Now you notice that this isn't quite symmetric. The reason for that is I'm using a shell mesh, not a solid mesh, so that is going to throw off our results just a little bit. If I were to switch to a refined solid mesh, you would see that this flow front would be much more symmetric, like we would expect. Another thing that you might want to get out as a designer would be a plot called ease of fill. And what this is giving us an indication of is based on the gate or gates and the location of these gates, how easy is it to fill the volume of the part in our injection mold tool. All right, so that is, let me switch to one last configuration here. We'll go to the solid completed model. And I'm going to read in the flow results just to show you that if you use a solid mesh, you get a little bit much more, or a more balanced gate filling contribution, if you will, using solid elements. Okay, so that is basically an introduction to SolidWorks Plastics Premium. And so what we did today is I showed you how to set up basically models with Plastics Premium using both shell and solid mesh. I did not show you a design change, so let's go back and do that quick. Go back into SolidWorks, and we'll go into this mushroom file here. We should still have the results for that. So let's go back in. Let's do the original. All right, so we had our results with this particular model using a shell mesh. So let's go in, change our SolidWorks model where we're going to change the value of this fill-in. So it was 15 thousandths of an inch. Let's make it 35 thousandths of an inch for our design change. So you can see that that really changed that cross-section right at the end there of this particular part. So we'll rebuild that. And now since I've changed the model, just like I would have to do in a finite element analysis, I have to re-mesh the body of this part. So we'll use our previous meshing parameters. Let's make it a little bit finer than that. Choose our material, flow settings again, and our gate location. Oh, that didn't add the gate. Sorry about that. Yes, it did. Sorry about this. Just need to add the gate there. And we should be good to go to run our flow analysis. So very quickly, inside SOLIDWORKS, any design changes that you make, we can reanalyze just by remeshing our model, resetting up our gate location, and then comparing the results. So we'll let that run in the background.